Welcome back to electrical point. In this video we will solve two problems related to motor rating based on equivalent current, torque and power method that we have discussed in the previous video. Please do watch the previous video before solving these two problems. Okay, these are the two questions that we are going to solve. In the first question, the torque profile is given. You can see that the torque profile is given and we have to find the rating of the torque and power rating of the machine. Okay, and in the second question the load profile is given in terms of power. Okay, you can see that kilowatt is given and we have to again find the power rating of the motor. And this question is little tricky, as you can see that the load is varying in these two interval here and it is, and also here the load is varying from here the 200 to 500 kilowatt and from here 400 to 0. And also it is given that the loss is proportional to the power square. We will also see the significance of this statement while solving this question. Okay, so this is the first question. It says that a drive consisting of semiconductor feed DC motor. So it's a question of DC motor run according to the following periodic duty cycle. The duty cycle is given in the first 10 second. In the first 10 second, it is in uniform acceleration and the speed increases from 0 to 1000 rpm. In the second interval, the duration is 8 seconds. Okay, and it is running at 1000 rpm and 800 newton meter torque. The torque is given and it's running at 1000 rpm, and again during the next 10 seconds the speed reduced from 1000 rpm to stand still, and in the remaining 20 seconds it is idle. Now you can see that it's a constant, the speed of the motor is constant. Okay, so it's a constant speed drive. Okay, first we got this. Okay, now we have to find the rating of the machine. This is the question, and also it is given that force cooling, assume force cooling. This is important, as I have already described in the previous video that whenever force cooling is given, we can use the equivalent torque, power and current method to solve this type of question. And also it is given that constant field current. Okay, it suggests that the torque, that's the torque profile that is given, the torque is directly proportional to I have discussed all this thing in the previous video. Now we will solve the question step by step. In the first interval, okay, in the first interval you can see that the machine is accelerating from 0 to 1000 rpm, and also given that uniform acceleration. We have to find the torque in this period. Okay, we don't know the torque, we have to find it. For calculating the torque, we will use the dynamic torque equation. You can check my video on dynamic torque equation in this playlist. It's in lecture number 2. Okay, so tau, that is the torque, will be equal to J d omega by dt. Okay, J is given as 1000 kilogram meter square. Okay, we'll put this value, 100 into, and speed is changing from 0 to 1000, so change in speed will be 1000 minus 0, and change in time will be how in 10 seconds. Okay, so time taken is 10 seconds, but this 1000, okay, 1000 is in rpm, and we have to find the torque in newton meter. Therefore we have to change the rpm into radian per second. This is the SI unit, we all know this. The relation is radian per second will be equal to rpm into 2 pi by 60. Therefore we have to multiply this value by 2 pi by 60. Okay, Now if we solve this, we'll get the value of T1, this is T1, tau1, sorry, that is the torque in the first interval, to be equal to 1046.67 Newton meter. Okay. Now in the second interval, it's running at constant speed, that is 1000 rpm, and the torque is given as 800 Newton meter. 800 Newton meter. We don't have to calculate this, and the time is 8 seconds. It's running for 8 seconds. Okay. In the third interval, you can see it's breaking from 1000 rpm to standstill in 10 seconds. The torque will be same as that of the first case. As it is reduced, the speed is reduced from 1000 to 0. But if you will solve this also, tau 3 will be equal to 100 into 0 minus 1000. Okay, as the speed is decreasing, the torque will be torque come out to be negative. Okay, into 2 pi by 60, this will be 1046.67 Newton meter. Now in the fourth interval, torque is 0 as the machine is in idle condition, and it's the time is 20 seconds. Okay. Now we have we got all the torque value. This one is tau1, this one is tau2, tau3, tau4, and all the time interval. Now I have already told that it is a constant field current. The machine has a constant field current. Therefore, tau is directly proportional to I. We can use the equivalent torque value similar to the I, similar to current that I have already discussed in the previous video. Now we will find the torque equivalent. Now the torque equivalent will be equal to tau1 square T1 T2 per square T4. Okay, have the total time here. We'll put the values. Tau1 is 1046 point, and the time interval was 10 seconds. Tau2 was 800, time interval was 8 seconds, and tau3 we found to be minus 1046.67 square, and the time interval was 10 seconds. The rest is 0. Okay, and the total time will be 10 plus 8 plus 10 plus 20, 10 plus 8 plus 10 plus 20. If we solve this, we'll get 750.42 Newton meter. Okay, now this is the torque equivalent. This is also called the RMS torque. Okay, as we are squaring the torque value over the time period, and then we are taking the root. And now as I have already discussed in the previous video, now I will see the lambda. Okay, now lambda is tau max divided by torque equivalent that we have found calculated. Now tau max, you can see from this intervals that in the first and the third interval that torque is 1046.67, which is the maximum torque. Therefore tau max will be 1046.67, and tau equivalent we found to be 750.42. This is less than 2. Therefore we can say that this torque equivalent will be the rated torque. Okay, so the tau rated will be 750.42 Newton meter. So this is the answer. And also in the question we have to find the power rating. Okay, now here I am solving this. We can see that this is a constant speed drive. Okay, therefore the power and torque relation will be power rated will be tau times the speed, and the tau will be the rated tau to find the rated power, and speed will be, this is 1000 rpm. It's the as the driver is running at 1000 rpm. Okay, and then we have to solve it. The tau rated that we have found is 750.42 into speed will denote by the omega. Okay, speed was 1000 rpm, but as I have already told, we have to change the speed into SI unit. We have to multiply by 2 pi by 60, and when we solve this, we get the power rated will to be 78.54 kilowatt. Okay, so this is the answer of this problem. So tau rated, that is the torque rating, is 750.42 Newton meter, and the power rating is 78.54 kilowatts. Okay. Now coming to the second question, you can see that it's a question of constant speed motor. Again, a constant speed motor is given, and the load profile is given in terms of power. Okay, you can see that kilowatt is given, so the load profile is given in terms of power, and also it is given that loss is proportional to power square. Okay, so loss is proportional to power square is given. We know that loss is I square, basically the I square R loss. As it is a constant speed motor, then we can replace loss to be proportional to I square R. Then it is also given that the proportional to power square. It suggests that I is directly proportional to P. So as I have already discussed in the previous video, we can use the same equation that we have derived for I equivalent to calculate the P equivalent. So we will in this case use this equation to get the P equivalent. Okay, that is P1 square T1 P2 square T2 up to Pn square Tn divided by the time interval. This P equivalent is also known as PRMS, that is the RMS power over the time interval, as we are squaring the powers over the time interval, and after that we are taking the roots. Okay, this basically gives the same heating effect. Okay, same heating effect as that of the load profile. Basically we will replace this P equivalent, the varying load, by P equivalent, that is the RMS power. Okay, now we will solve the equation in step by step. Now in the first interval, we will see the first interval, that is in the starting 4 minutes. Okay, now you can see that load is rising linearly from 200 to 500 kilowatt. Okay, so the load is rising from 200 kilowatt to 400 kilowatt, and it also given that it is rising linearly in 4 minutes. Okay, therefore the rate of change of load, okay, is 400 minus 200 divided by 4 minutes, that is 75 kilowatt per minute. Okay, this is the rate of change of load. Okay, now we know the rate of load change, and so at any time t, the instantaneous power pt in the first interval will be 75t plus 200. Okay, we are basically using the linear line equation, that is y equal to mx plus c. This is the rate of change. Okay, and c is the intercept, which is 200 in time, t equal to 0. If we put value t at t equal to 0, we will get that the load is 200 kilowatt, and if we put p equal to 4 minutes, then we can get that the load is 500 kilowatt. Okay, now we know the pt. So the equivalent current, equivalent constant power in the first interval, that will be the RMS power. So basically we will find an equivalent value of this power in that time interval. So PRMS 1 will be the P1, and this is under root 1 by T 0 to T Pt square dt. This is the equation of RMS power. Now we'll put the values. 1 by 4, 0 to 4, this is 75t plus 200 square dt, and if we solve this integral, we can solve it using a scientific calculator. The value of P1 will be 360.55 kilowatt. Okay, so this is P1. Now coming to the second interval, it is given that uniform load of 400 kilowatt. Okay, for 2 minutes. Okay, so P2 is 400 kilowatt for 2 minutes. Now in the third interval, again it is given that regenerative power returned to the supply reducing linearly from 400 kilowatt to 0. So again we have to use, in this interval we have to use the concept that we have used to find the value of P1. Okay, now we'll calculate P3. Now in case of P3, the load is reducing from 400 kilowatt to 0 in 3 minutes. Okay, so again we'll find the rate of change, rate of load change. Okay, that is 0 minus 400 divided by 3 will come out to be minus 400 by 3 kilowatt per minute. And again therefore the instantaneous power T Pt in the time interval will be 400 minus 400 by 3 T. So if you put P equal to 0 here, that in this time interval at 0 minute it will be 400 kilowatt, and at P equal to 3 minutes it will be 0. Okay, now we'll again use the same RMS equation to calculate P3, that is under root 1 by T 0 to 3 400 dt. Okay, now if you solve this equation, we will put this value. This is 1 by 3 this is square. If you solve this value, then P3 comes out to be 230.94 kilowatt. Okay, now in the we have found P1, P2 and P3. Now in the fourth interval it is given that it remain idle for 4 minutes. Okay, so P4 is 0 kilowatt. Now we have all the power value and all the time interval. Now in the next step we will calculate P equivalent. Now P equivalent is P1 square T1 plus P2 square T2 plus P3 square T3 plus P4 square T4. Okay, and divided by the total time, that is 13 minutes in this case. Now if we put all the value, P1 was 360.55 square into time interval was 4 plus 400 square and 2 minutes. In the third interval the power was 230.94 according to 3 minutes plus 0. If we solve this, we'll get the power equivalent to be equal to 277.34 kilowatt. Okay, this is the P equivalent. Now we will calculate lambda. Now lambda is P max by P equivalent. In the first interval the load was rising from 200 kilowatt to 500 kilowatt, so the maximum power is 500 kilowatt in this case, and the P equivalent that we have calculated is 277.34, which is less than 2. Therefore the rated power that we have to calculate in the problem is 277.34 kilowatt, and this is the answer. Okay, and that's it for this video. Please do like, share and subscribe the channel, and stay tuned for more concept related to electrical types. Okay, thank you.